All right, let's go ahead and get started. I do want to welcome you to this installment of General Equilibrium. We're continuing with our march through the Rice tables, and it is absolutely critical that you follow along with the calculator, especially, and make sure that you know how to enter these things into the calculator. So let's go ahead, and don't let your neighbor do the work for you either. You need to actually do the work. So here we go. This is problem number 2. Here's what it says. It says a vessel initially has a partial pressure of NO equal to 0.526 atmospheres and a partial pressure of Br2 equal to 0.329 atmospheres. So this is a problem using Rice tables that we'll approach using pressures. And so it says at equilibrium, the partial pressure for Br2 is, I've got a typo on my sheet. You should be okay on yours, but it should be the concentration. I want the partial pressure of the Br2 to be 0.203 atmospheres. That's what it should say for bromine gas, 0.203 atmospheres. Now, it says calculate Kp for the reaction. Calculate Kp for the reaction. So here it is. I'm going to save a little bit of time in my Rice table by just putting the R right next to the reaction itself. I've got 2 moles of NO gas plus Br2 gas in equilibrium with 2 moles of NOBr. Of course, that's a gas. So everything's gaseous. So they've told me that the initial the initial pressures for the NO and the Br2 respectively were 0.526 atmospheres and 0.329 atmospheres. And no mention has been made of NOBr. So that means that there's no NOBr, right? There's nothing there. So that means that in the change line, the equilibrium is going to shift to the right. Now, I don't want you to get the idea that equilibriums always shift to the right. They don't. But they always shift to where there's nothing. So NOBr has a 0 in the initial slot, right underneath the NOBr is a 0. So you know the equilibrium is going to shift that way. So in the next line, we're going to put a plus right there, right? We're going to put a plus under the 0. So plus something. I don't know what it is yet, but plus on this side. On the opposite side is where the negatives go, right? On the opposite side, I put negatives just like that. So then what I'm going to do is I'm going to use the balanced chemical equation to tell me what is going to go in front of the axis. So in the balanced chemical reaction, I've got NOBr, and I've got a 2 in front, so there'll be a plus 2x there. For the Br2, it's minus, and there's no coefficient, so I'll assume it's 1, so minus x. The same, actually for NO, there's a coefficient of 2, so I'll put minus 2x on that side, and now I've got my C line figured out. Let's take a look at the equilibrium line. To get the equilibrium line, remember, I'm just going to add up the initial line and the change line. So we've got 0.526 minus 2x for NO. For Br2, we've got 0.329 minus x for this one right here. And for the last one, we've got 0 plus 2x or 2x. Now, I am told that at equilibrium, the partial pressure of the Br2 is this, 0.203. That's critical because that number is equal to the expression in the equilibrium line, right? 0.203 is equal to 0.329 minus x. And by the way, 0.203 is not equal to x, rather it's equal to 0.329 minus x. And so I can calculate x by setting them equal to each other to be 0.126. So now I know the x, 0.126. So I'm going to plug it in here. 2 times x is 0.252. So now I know the equilibrium, not the expression, the actual value. The actual number of atmospheres at equilibrium for the NOBr is 0.252 atmospheres. And I can do the same thing again with the 0.526 minus 2 times the 0.126, and I get this number, 0.274, just like that, okay? 0.274. So now that I know all the equilibrium pressures, I can plug into this equation. The expression is Kp is equal to the pressure of NOBr. Notice I do not use brackets. Okay? If you put brackets, I'll count it wrong. Right? That's for concentration. This is not concentration. It's pressure, NOBR, and we're going to square it because there's a coefficient of 2. Divided by, it's product over reactants, the pressure of NO. The pressure of NO squared, because again, there's a coefficient there of a 2. And then the pressure of the Br2, again, it's 1 right there, right? Now let me plug in equilibrium pressures. For the NOBR, NOBR is 0.252. I got that from right there. I squared it. PNO, I get 0.274. Don't forget to square it. And for this one, I get 0.203. Don't need to square it. And the value that I end up with is 4.17. Kp is equal to 4.17. And I'm done with this problem. Notice I'm not asked for anything else. I'm not asked for equilibrium pressures. And so I won't give it to them, right? So I'll just, at least formally, I'm going to say this. I'm going to say Kp is equal to 4.17, and I'll even box that to make things easier for everybody. But that's it. That's all I'm going to give. All right, so hopefully that one makes sense. Let's take a look at problem number 3. And so number 3, we'll look at it from a slightly different perspective. Here's what it says. It says the following reaction, and this time we have 2HI, that's a gas, in equilibrium with I2 gas, plus H2 gas. It says it occurs at 298 Kelvin. Now, if 2 moles of HI are placed in a 1-liter container and permitted to react at equilibrium, it is found that 20% of the HI has decomposed. Calculate Kc and Kp. So they're going to want both Kc and Kp. All right, we're going to take this from a Kc perspective since I don't have pressures, but I do have concentrations, or at least I can get them easily, right? I've got a, let's see, it's a 1-liter container, so that's going to be easy to calculate these concentrations. So let's set up our Rice table. Here we go. We have, first of all, the R. We have 2HI in equilibrium with I2 and H2. So that's my reaction. Now we need the initial concentrations. Well, they're telling me that I'm starting with 2.00 moles per liter. I'm just going to say 2. 2.00 moles per liter, but no I2 or H2. So that's it. That's all I've got, the HI and nothing else, right? So that's the initial concentrations for HI, I2, and H2 respectively. Let's go to the change row now. We've got, well, let's see. Remember, the equilibrium always shifts to the 0. I know you're probably thinking that it's every time it's going to shift to the right. It just doesn't. Just take my word for it. It's just that there's zeros on the right-hand side. That's the way it's going to shift. That's the direction it's going to go. So we're going to put pluses here on the right-hand side. On the left-hand side, we'll put a negative sign right there. We'll use the coefficients to tell us what goes in front of the x. So for the I2 and the H2, there's no coefficients, so we'll just say plus x plus x. But in front of the HI, there's a 2. So we're going to say minus 2x just like that. Now let's set up our equilibrium line. Here we go. 2 minus 2x for the equilibrium line for HI. I2 would be 0 plus x, and H2 would be 0 plus x, again, x. Okay? All right. So now what we're going to do is this. We've been told something that's very revealing here. It says this, and this is the tricky part. It says it is found that 20% of the HI has decomposed. 20% of the HI has decomposed. What does decompose mean? It means change, right? So they're giving me a little clue. They're telling me that this value right here represents 20% of the initial concentration of the HI, right? 20% of the initial concentration of the HI. So let me set up a little equation. What they're telling me is that 2x, that's the change. I'm not concerned about the fact that it's losing 2x. 2x is the change, is equal to 20%, 0.20 or 0.2, of the initial concentration, which is 2, right? Of the initial concentration, which is 2. So when I do that, I get x is equal to, these will cancel, 0.2, right? 0.2. So now that I know that x equals 0.2, this is 0.2, this is 0.2, a little typo here, let me fix that. Here we go. Let's see, actually, let's do it like this. We'll erase that 0 first of all, and that should be a 1. So that should be 1.6 right there. So now I think we've got it straight. So we've got now 1.6 the concentration for the HI. The I2 is 0.2. The H2 is 0.2. Let's set up our expression for Kc. So here we go. Kc then is equal to products over reactants, H2 and I2 over HI squared, right? HI squared. Concentration of HI squared. So now what we're going to do is plug in 0.2 and 0.2. I could have written 0.2 squared. Divided by 1.6 squared, this is the number that I get. We get 0.156. Okay, excellent. That's my Kc right there. I'm almost done, because they've also asked me for a Kp, right? So how do I determine the Kp if I've got the Kc? Well, there was a formula. Remember the formula? It was Kp is equal to Kc times RT delta N. But I asked you to try a little trick, and that is to look to see if the change in the number of moles from products to reactants was the same. So let's count the number of moles of gas. Well, gee, when we do that, we've got 2 moles of gas on the right, 2 moles on the left. The number of moles of gas doesn't change. That's going to save me a lot of calculation here, right? It's going to save me a lot of work, because now I know that 2 minus 2 is 0. So this delta N is 0, and anything to the 0 power is 1. So R times T is 1. That would mean Kp would be equal to Kc. Now I can't simply write that Kp is equal to Kc, because they have asked me for the calculation. So what I'm going to need to do is I'm going to need to actually explicitly write, copy again, Kp is equal to 0.0156, just like the Kc was, and that'll do it for this problem for me. That'll do it for this installment. I'll see you on the next one. Thanks. Bye-bye.